Hello everyone, my name is Nicholas Condon and I'm the Senior Microscopist and CZI Imaging Scientist at the ACRF Cancer Biology Imaging Facility at the Institute for Molecular Bioscience, the University of Queensland in Brisbane, Australia. This workshop is called Advanced FIJI and we'll go through some steps to automate processes, whether it's using plugins or using batch processing or scripting in the open source program FIJI. Firstly, if you are in Australia and in the light microscopy community, I can highly recommend signing up and joining to the Light Microscopy Australia subgroup of the Australian Microscopy and Microanalysis Society. Currently, prices are $50 for a full membership or $25 for student membership per annum. And this gets you reduced or free registration to conferences and workshops, and it lets you have your voice heard around the future of light microscopy in Australia. And in 2021, they're holding their virtual conference in August. So we'll count for that. Now, most people who want to automate tasks are following some kind of image analysis pipeline. And this pipeline usually involves a predefined set of tasks. This usually is a pre-processing step, which is filtering, background subtracting your data, segmenting your data, and then analyzing the data. And so there are a number of ways that these steps can be automated or incorporated into some kind of pipeline to speed up your workflow. So the first kind of main overarching theme is we want to automate our image analysis to speed up and make our lives easier. Well, why would we want to automate? Microscopes can generate lots of data nowadays. Whether you're screening compounds or some kind of genetic manipulation means that multiple comparisons are often required. So having a robust automated analysis is less biased and is most importantly more reproducible. Hopefully, sometimes it makes your life easier, and it can often be published as a follow-up methods paper or book chapter to your main publications that you've used these pipelines in. But, and importantly, developing these scripts and pipelines often requires you to have a bit of a cost-benefit analysis. What I mean by this is the time that you're going to spend developing the script and pipeline, will it take more than how long it would take to process, maybe if you only had 10 images? So if you have a small amount of data, sometimes manual is still best. But if you have lots of data, or maybe you're going to have a small amount of data, but you're going to have that every week, then automating it would certainly be worthwhile. But these scripts do take time to develop. There are three main types of automation in FIJI. The first one is to use plugins. Plugins are pre-built programs that run within ImageJ or FIJI. They're published and often peer-reviewed and are really useful at automating common tasks. So you can use these so that you don't have to reinvent the wheel in every single analysis that you do. And there's different plugins for visualization, segmentation, or tracking. And we'll go through some of these in the future slides of the workshop. Secondly, there's batch processing. This is best used when you want to perform an equal task on all images within a folder and put them into a new folder, for example. Maybe you want to scale all the images. Maybe you just want to perform a max projection on them. Lastly, there's scripting. And scripting or macro programming is the input language that can be custom written. It allows for logic and branching of your code. So using Boolean statements, if this, then do this, or for commands. So for every image open, do this. And it can be written and read in multiple languages, including Python, Java, or ImageJ's own language. And these are for custom complex workflows and analysis. So the first kind of area is the plugins, or as I like to call it, using other people's tools for your automation. It's important that when you install plugins that you can update them as well. Keeping everything up to date is a must for ImageJ and FIJI. So to follow these steps to ensure that everything's running the latest of versions. Under the Help menu, you can select Update. When you run the updater, it might say certain updates require changes, so you can apply them. If you'd like to explore more options that are being actively updated and plugins for FIJI, click the Manage Update Sites button down the bottom left. In here, there are simple tick boxes that you can turn on for the items that are of interest for you. If your collaborators or the plugin of choice is not in the list, you can simply add an update site and enter the URL for that. Sometimes plugins might be from outside of FIJI and you want to install them. These can be downloaded from websites, and these websites are sometimes listed on the wiki page. And to do this, it's an absolute requirement that your FIJI or ImageJ is installed where you can modify things. So if your institution has given you a computer and you don't have administrative rights, you might need to talk to your IT team to have a copy of FIJI that you can edit on your own. So firstly, you're going to download the plugin file to your computer. Usually the wiki page will explain who made it, how to cite that plugin, how to use it, what version, when it was last updated, etc. Next, you can navigate to your FIJI or ImageJ applications folder. If you're on a Mac, you can go in and say show package contents, or you can navigate directly there if you're on Windows. Move the downloaded plugin into the plugins folder within there. You'll have to close and reopen ImageJ for it to be installed. Some plugins can also just be launched into FIJI by dragging them onto the taskbar, and then FIJI will prompt you to save that plugin into that folder. So the first exercise is to install the following plugins, because we're going to look at these and use them in the workshop. You may have some of them already in your default build of FIJI, but either way, I'll quickly now show you how to do get these plugins. If you want to do it on your own, pause the video, and then we'll come back and show you that. So once you have FIJI open, you can go to the Help menu and navigate to the Update. FIJI will go through all of your plugins and check if they require updating, and then download those files if you need them. Depending on the number of plugins that you have installed in your FIJI, this can take a very short amount of time or quite a while. So we can see that my FIJI requires some updates. If you want to add some of these required plugins for this workshop, you can open up the Manage Update Sites and scroll through and simply tick the items that are listed on the slide previously. You can see that there is a large number of plugins automatically available here for you. When you select those tick boxes required, the list here of actionable items will obviously increase, and then you can say, okay, apply changes. FIJI will then go download everything that's required and install them for you. Once you've updated and changed the files within the FIJI or ImageJ folder, you have to restart it so that they'll take effect. So we can close ImageJ. Once FIJI restarts, in your plugins folder, you should see the plugins that you've selected are available to be used. The first plugins that we'll be looking at in this workshop are visualization-based plugins. There are 3D volume viewing plugins in FIJI. There are a number of these. These have not been developed by me, they're developed by other people, and they have, different niche markets where they really excel. Often, viewing 3D datasets in FIJI can be challenging. There are lots of plugins that exist, and each of them have good and bad features and functionality. None of these plugins were made by myself, as I said, so if you use them, they were made by other researchers, and I would very much encourage you to cite them. The 3 that we're going to look at today are the Big Data Viewer, the 3D Viewer, and Clear Volume. The Big Data Viewer is very responsive with big data sets, as its name suggests, and it's great for reslicing, cutting, and transforming your data. But it's not very good at volume viewing your data, and it can record animations, which is quite nice. The 3D Viewer can be a little bit laggy with big data in my hands, but it's great for surface rendering and interactive volume viewing of some smaller data sets. It doesn't have reslicing or cutting available in it, and you can record animations. Clear Volume is okay with big data. It's great for interactive volume viewing and on-the-fly display adjusting. It has some cropping available, and record interactive animations is possible. So the first one is Big Data Viewer, and this will be located under the plugins, Big Data Viewer, and then Open Current Image will open the image that you have open into the Big Data Viewer window. In the top corner of the viewer, we can rotate and see where we are within our data sets. Down the bottom, if we have a time series data, is a slider, and these are pulled from the wiki about some of the different keyboard shortcuts you can use to navigate around the data. The 3D viewer will be under Plugins, 3D Viewer. And when you launch this, you'll get a window to say, which image would you like to add? What is the name that you'd like to have it? How would you like to display it? The color that you would like to display it, or any threshold value to include with the rendering, and whether you want to scale or downsample the data. Once you've chosen the option of choice, you'll get a window similar to this one, where you have some tool menus up the top so you can change the display or the display color, and you have a time series slider down the bottom, which is quite nice to navigate through. Lastly, Clear Volume will be located under Plugins, Clear Volume, and then Opening Clear Volume. The first time you use this, you might get a warning about having FIJI or granting access to the GPU for FIJI. And when you launch your data in, you'll receive a window like this. You can adjust the voxel size if required. You can perform interactive 3D cropping on the data sets. You can view the recording tools and change the visibility of the gridded box. You can channel toggle on and off and change the transparency levels and color tools, and you can adjust time across here. Now down the bottom, we have these interactive display adjustment tools to help tweak your display settings for any animations you may want to record. So the second exercise is to try the 3D volume viewers that we've just gone through and that you've installed in your version of FIJI. There's a folder called Exercise 2, Try 3D Volume Viewers, and there is some data sets in here that you can use to open and preview. Again, pause the video if you want to try this on your own, or I will lead you through it as well to show you some things. So the task would be to trial the different plugins, see if it's possible, or see what's possible with the open source and free software. This first example data set is a zebrafish. This second data set is an example of some macrophages captured on our lattice light sheet microscope. So if we first open the big data viewer, we can say open current image. We'll select the lattice time point data sets for these examples. We have our window. We can rotate our view through the data set so that we can reslice it interactively. We can see at the top here that we can also use the navigator to choose a slice through the data set. There are a number of settings where we can change the brightness and contrast, where it will open up a window here. And we can adjust the values that we want to display so that we can see our data set quite nicely. If we open the same data set using the 3D viewer, we have our options window. So we're going to choose that lattice light sheet example time point. We can display it as a volume or a surface, what color we want to display it as. We'll turn off any of our RGB colors for the moment, and we can click OK, and it will open the data in the viewer. Now we can see that the status bar is doing something in the background before we see our surface render. Now we can go ahead and change the threshold down to a lower value to take more of the data, so more of the intensity range, re-render that data, and now we can see the whole cell surface and all of the fluorescence that was captured. We can resize this window, and we can move around the data. And, we can see the surface features, and it may not be as smooth as some of the commercial packages that you might be familiar with, but this is free and you can do it on your own computer. You don't need licensed software. Lastly, we can open up the clear volume. Now this is at the bottom of the plugins window, or you can search for opening clear volume. We'll see that it's loading up the data sets into the clear volume viewer. We can zoom in and out, and we can rotate the data around. Now it's displaying it as a MIP mode projection. We can crop our data set down to our volume, down to an area that's more representative of the field of view of cells. And you can imagine that you can use this to kind of show inside features. We can turn off the box, and we can move the data around. What I personally like about this viewer is that you have the option to adjust the brightness and contrast very dynamically, and you can adjust the gamma to kind of fill in and get a pseudo kind of full 3D view of the data set quite nicely. Now, all of these have recording options. With the clear volume, you can start and stop a recording, which takes a series of images that you can then import as a sequence into FIJI again to then turn into a MP4 or AVI animation. So that's a very quick overview of these different plugins, just ways to kind of explore and view your data that you may not knew was possible with the free open source software. Remember, if you are using these plugins for your research and publications, you should cite them, and the information is on the slides, or you can look up the wiki pages for these relative plugins, and it has all the information about the publications and the citations. Okay, so we'll close these and go back to the PowerPoint. Now, the next step that you can use in your analysis pipeline is segmentation. Segmentation can be done using thresholding or analyzing particles or manually drawing and creating selections. If you have lots of data sets or you have complicated data sets, you can use some existing plugins that have been published to segment your data quite nicely. And one that we're going to demonstrate here is a relatively new plugin, and it's called StarDist. And this works really well at segmenting nuclei using a deep learning algorithm. It can perform this on 2D and 2D over time data sets. And it was developed at the Max Planck Institute by these researchers. And remember, again, cite these plugins if you're using them. But I find in my hands, it's very excellent at finding nuclei with even very difficult samples such as tissue where there are lots of nuclei. It automatically adds your segmentations to the ROI manager, which is great for a lot of downstream applications that our researchers here have. And it works on fluorescently labeled nuclei and some bright field like H&E type staining straight out of the box with no real user input required. We'll be performing a workshop later in this year, 2021, which will cover in a bit more detail StarDist. So look out for that. So this is some example images of what's possible. So I have here a part of a heart section that's been stained for DAPI, and you can see that there's a lot of nuclei. And the StarDist does really well at segmenting each of these individual nuclei automatically. And then we can feed this into downstream applications where we have researchers, with transcription factors that they're looking at, and they localize to the nucleus, so we can capture that quantification really easily by incorporating StarDist into our workflows. So in this third exercise, we'll be opening up the heart tissue example data, and we're going to see how well StarDist works. And so you've likely only just come across this, and you can see that this is really nice, a deep learning method that speeds up your workflow. So again, if you want to pause the video and try this yourself, otherwise I'll go through it. So we're going to open the example image files and trial the different StarDist models on the images to see how it goes with segmentation using deep learning. So we can open up the example image for the heart. We can zoom in and we can look at this data sets and see that there's lots of nuclei in this image. And this is a tile image of a whole heart section. So in the interest of time, you may want to just duplicate out a small region. So we can take all these nuclei here and go plugins, segmentation, So we can go StarDist. We can use the 2D plugin. And we get this window. Now you can read up on the help page and the wiki page on a bit more information about the different models that are available. So we can use the fluorescent nuclei model. And we can run that. And we can see that it's running the network. it's opened up our labeled image with all the nuclei that it's found, and it's added them to the ROI. So we can show them and see that it's doing a very nice job at identifying these nuclei. Now, obviously, if you run this on the whole field of view, it's going to take a little bit longer to process all of those segmentations. Now, you don't have to use it on a tissue section. You might have an image where you just have a number of nuclei from transfected cells, for example. So here we've got a DAPI stained image of a number of nuclei. We can go back to that StarDist. And click run. Now, normally you could go into the plugins and scroll down to select it. I have so many plugins that they're not displaying on my window, so I'm using the navigation and the search tool to bring them up. But you should be able to just scroll down to plugin StarDist and run them. So running that network again on this image, where obviously there's fewer nuclei than before. It's very fast. It's found our nuclei, and we can see that it's doing a really nice job of selecting them. And this can be certainly in my hand better than just running a, some background subtraction and then the smoothing and then a filtering with, a threshold, and then perhaps you run a watershed. That can work quite well, but when you have lots of images with lots of, nuclei, this method is certainly faster and more robust. So if you find that you use it, again, please cite the paper and the researchers, and we will continue on now. Now, another method of plugins that you may want to use is tracking. So there's a plugin in, one of the plugins in FIJI that I've used quite a bit with different projects and is very well written and runs very smoothly, is the TrackMate plugin. So there's a quick screenshot of all of the contributors and the URL and the information about how to cite it. Now, when you launch TrackMate, you get these windows, and it's like a little wizard that walks through different steps of the process to then give you something that's quantifiable. So that's the overview of TrackMate. It works in a wizard-like way. It's very friendly and intuitive in the way it's designed and very easy to use. So it will be in the plugins tracking TrackMate. And it works through these steps where you basically detect the objects, you filter out objects based on size or location, you then track them and you can filter on the tracking, and you can perform the component analysis and you select what you want to output. So in the example of some algae that some are swimming around, and we had a researcher here who wanted to track them, we would work through it using the following kind of process. The first thing is to identify the spots or the objects. And you can do this based on their size and some threshold information. So how bright they are above the background, whether you want to do any kind of filtering beforehand. It will then tell you, how many spots that it's found based upon your selection. You can then set some filters. So, one of them might be quality. If you don't select them on the slider, then they're going to be discarded. The third step is to choose how you want to view it. So do you want to use the 3D viewer? Do you want to use hyperstacks? Then you can filter out your spot selections again on things like quality, their size, their intensity, their position. All these many options are available from the dropdown. Then you can choose the different tracking algorithms. And if you read the wiki page, it goes into a bit more detail, but you get a very short description here describing what the different tracking algorithms are. Then choose the settings for your tracking. So These will vary slightly between the different algorithms, but what's the linking distance? So the distance that are allowed between frames. There's the gap closing. So the distance that's allowed when the spot's not detected. So maybe in one frame, it didn't pick up that object, and we can see that it's moving in this direction. So we can add that. And you can just have the number of frames where it is not detected at all. Lastly, you can apply filters on the tracks. So while some objects might not be moving, some might be moving a lot, you could filter by the length or the displacement of your tracking. So maybe the object's whizzing around in a circle and it might move further than these long ones. So maybe you want to say how far it's actually moved or the duration that it's tracked for. There's lots of options again. And again, it's very intuitive. Lastly, there's the track settings and management. So do you want to create a plot? Do you want to link different tracks together? Do you want to explore the tracks in a new window? So there's all options here. And then you have your outputs. So do you want to have an overlay image? Do you want to export some data to a spreadsheet to then do some quantification on? Do you want to export the tracks to other programs and workflows like IC? So in the fourth worked example and exercise, we'll go through TrackMate, where we have some example files of these the algae, and we're going to walk through the wizards as I showed on the previous slides and export a spreadsheet with some of the data. So if we open up our tracking TIFF file, we have these algae that are moving around. We can go to our plugins, tracking. We can run TrackMate. So we're going to detect our objects firstly. Make it a little bit bigger. We can preview what it's finding. That's obviously way too many. So we need a threshold value to only see certain objects. So we can see that these bright objects are being found, maybe not these background ones. But for this example, that should be enough. So then it goes through and has found all the detection of all the spots over time. We can change the threshold if required. We're going to view it as the hyperstack. We can apply some filtering if required. So we can say we want to filter based on the time frame or the radius, all these many options. So we can adjust these by sliding, or if we change the option, we can choose from the below. So let's pick most of those slices, or we can auto calculate, and then we can continue on. There are a number of different algorithms that we can choose from for the tracking. We're just going to use the simple tracker. You can choose the amount of distance between frames, where the distance where it's missing, or the number of frames where it's missing between. And you can see that we get some tracks. Now we can still navigate through, and we can see that, for example, in this algae here, we don't have a complete track of it. So maybe we'll go back, allow more frames to add where it is. Perhaps the quality was too low. So if we go back, we can remove that filter. And now we can see that that algae is tracked all the way through the video. We can add filters to our tracks, so we can say, I only want different velocities, or I track displacement. So we can see that if we take everything, these little cells that aren't moving around very much, maybe we aren't too interested in those, and we're only interested in ones that have gone through a large displacement. We have some options to display, so we can increase the radius of our spots. We can say that they're uniform colors. We can show the different tracks. We can set the color by not only just the track index, but by velocity or other kind of quantifications. So if we just set it to track ID, it's unique for each one. We can see the track scheme, where you can track the objects over time. And you can see when the tracks appear at what time point and get some information there. You can perform analyses, so you can get statistics on this information. So the track ID, what its source, its location. You can see the other kind of things like the number of spots, the number of gaps, all these information, the speed between frames, lots there. And as you select on them, you get different tracks highlighting. So we can modify these and edit them and view the spots and view different plotting tools, so we can see different schemes. Lastly, we can perform exports, so we can export the statistics. We can run that and we get a file that can be saved. As a all spot statistics CSV and save it out. Now, obviously, this is very dependent on your application, but many people don't realize that plugins like this exist and have been written for ImageJ and FIJI so that you can track objects over time or movement using these tools. So perhaps you have cell migration and you could apply StarDist to segment the nuclei and then track those nuclei using this in a kind of wound healing or scratch assay. And so if you do combine TrackMate with other parts of your workflow, remember to cite it. And now you can hopefully see that using some of these tools that have been developed by other people and are available for you to download and use, you can do a lot of tasks really robustly, repeatably, and you don't have to code at all to do this. But maybe you want to create your own automation. And you can do this in two ways: the batch processing method I described earlier, or by generating scripts. In FIJI, everything that you do is usually a command. Commands can be strung together into a type of recipe for multiple steps. So perhaps you want to run a median filter and then max project your data. And your data here is 500 Z-stack images. There's two ways that you can kind of find the commands to do this. There's a tool called the command finder, or there's the macro recorder. You may need some basics for coding that you're going to have to think about, like using variables instead of file names, and that it's important to always have some kind of output for your scripts, usually the steps, not just the outcome. So sometimes you might have a process where you generate all these data, and sometimes something weird might go on and you want to know what happened. So having the thresholded image of a mask saved out can really help troubleshooting things. There's the command finder. The command finder is kind of the I know what I'm looking for. So you can go plugins, utilities, command finder, and you can search. It shows the path to where it is. It's executable. It links to the source information and the wiki pages online. It's very nice. But coding shouldn't be scary. So if biologists can figure this out, then I'd say almost anyone can. And I'm a biologist, and this is how I learned the FIJI macroing. So in FIJI, you can get the command for what you've done by using the recorder. So this is kind of, I know how to do it, but I may not know what it's specifically called. So you can run the task that you want to code, and it generates it here in this recorder window under plugins, macro, record. There's batch processing. And what batch processing does is it allows you to quickly repeat certain commands on all your images within a directory. It's great for simple commands and processes. Perhaps you have a bunch of files in a bioformats format like CZIs, and you want to just quickly convert them to TIFF. Well, you can do that with the batch processor. If you just want to perform a Z projection on all the images, you could do that in the batch processor. Maybe you want to recolor all of your images to a certain LUT, or change channel 1 from being red to being magenta and channel 2 from being green to be cyan. You could do that using a batch processing tool. But if you're going to be creating lots of windows and lots of results tables, it's not really suitable for a batch processing. That's more a task for a macro. So the workflow for batch processing would be to, open an image that you want to do these tasks on, an example image. And you might want to say, open the image, reset the brightness and contrast, run a maximum projection, and make sure it's displayed as composite. So you could do those tasks and have the recorder running, and you would get something like this. If you click on the window, it's going to say, select this window called control blah, 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 .dv from Delta Vision. Then we wanted to reset the maximum and minimum. So then that would be, we've gotten this command, set min and max to the full dynamic range of that image. So that in this case, it's a 12-bit image. So the minimum 0 and the maximum is 4095. We wanted to then run the maximum projection. So this is the command run Z projection with the projection type maximum. And lastly, we wanted to display it as a composite. So the command is set display mode composite. Now, if you just read these commands, you'd probably be able to figure out what they're doing, because the macro language in FIJI is very self-explanatory, and it's a very basic coding language. But sometimes we have to think about the code that some of it that generates in this recorder window might not be useful. If we're going to perform this on multiple images, we want to look for code that's included here that's really specific, and that might cause an error. So make sure that you don't include this in your batch commands for batch processing. And in this case, that select window with a very specific file name will cause an error, because if this was the first file, it would run fine. Once it's closed and it's opened the second file, it's going to try and look for this file that won't be open and cause an issue. So you would copy that text that's relevant into the batch process window. So this is the batch process window. It's under process, batch, macro. And you can see, again, it's quite self-explanatory, but you have an input directory location, an output directory location, what the output format is. So whether you want it to be TIFF or 8-bit TIFF or raw images. If there's any common macro code commands, or if you want to provide a filter. So maybe you have, for example, a image file, and then you have a .xml metadata file, and you have lots of those. You might want to include that the file name contains .tiff or .czi or whatever the file extension might be. Alternatively, maybe you have lots of images and some of them are called control and some of them are called treatment, and you only want to look at the control images first. You can put a filter for the word control. Lastly, you paste your code in here and you can click process. If this is a command series that you're going to be running often, maybe you want to save it so that you can bring it back later and reload it. Remember that this is a method that's really useful for just bulk handling of data sets. Everything's treated equally in the same way. If you're going to run a median filter, it does it on every image. There's no if this, then that, or outputting of results as well. That's more for macro and scripting. So in exercise 5 in this workshop, we're going to run a batch processing task. There's a folder, exercise 5, that has a series of Z-stacks from the example data set called mitosis. So in this, there are about 50 frames of files that are going to divide. So let's perform the following processes on them. We're going to apply a median filter of 2 pixels. We're going to then scale that image up 2 times in X and Y, and we're going to perform a maximum projection and save that output into a new folder within the parent directory. Median filters are under the filters submenu of processing, and scales under the image menu. Perform that task now. We have our input files, so we can open up one of those files and we can see that it has 2 channels and it has 5 slices, and that there are 51 of these files in this folder. So if we go plugins, macro, record, we have our recording menu open. Now we want to run a median filter, so we can go process, filters, median with 2 pixels. We can see that our image is now a bit more smooth or blurred, and that we have the command in the recorder. Next, we were to scale the image. So under image scale, we're going to scale it 2 times in X and Y. Now our image is slightly bigger than the original, and we're going to perform a Z projection that's of the maximum projection type. And we have our commands. We can copy those commands, go process, batch, macro, and we can paste in our list of commands here. So we're going to run a median filter with a radius of 2. We're going to run the scale with these settings. Then we're going to run the Z projection of maximum intensity. So we can choose our input directory. So in this case, it's the batch processing folder, input files, and our output file directory we can make called output. We can select that. Then we can do this. We can see that it is processing. We can navigate to our folder, see that in the output, these are saving along and it's completed. So we can open that and we can see that it's a 2D image and that they've been flattened and blurred. If we wanted, we could quickly import those as a sequence. So we can run import image sequence on our output folder. There's 51 images. And we can see that it's loaded them alternately. So we can come in here and go stack to hyperstack. There's only one Z. There's 2 channels and 51 frames. You can see that our red and green channels are available and that we can view it as a composite and see that division occur. So that's a quick way to string together a couple of processes that you might repetitively do on your files over and over. Now, the next way is to do more complicated tasks is scripting in FIJI. Now, this is a very quick overview on scripting. It will highlight the benefits, but it will not teach you how to code from start to finish. That would be in a future workshop that I'm currently developing. Some of the benefits of scripting are that they help to speed up your analyses or workflows. It's really robust and unbiased. It does the same thing every time. So if you run the same script today, tomorrow, and the next day on the same data set, it will give you the same results. It can streamline these complex workflows. And as I said earlier, it's often publishable because if you spent the time to create this, often someone else may benefit from it. The script editor in the version 2 of FIJI includes autocomplete, which makes it really easy to kind of build up some code. It's very helpful and useful. Some of the commands also include the parameter requirements. So in this example below, when you type dialog add choice, it says that you need a label and the items, and there's a description that explains what this command will be for. It now also has user-defined variables, so it makes coding a lot easier. When you define something as a variable, it then shortcuts to that as you type it and refer to it later on, so that there's no spelling mistakes or case issues. It has nice shortcuts as well for things like for loops, where it auto-populates it with some generic parameters to help get you started to run these complex tasks. So you can go File, New, Script, and you'll open up the scripting editor. Now, most scripts generally follow a defined workflow or pipeline. For example, you usually want to define your input directory. So where are the files that you want to process? Then you may want to define some kind of output directory. Well, where do you want to put the files and the analysis results after the fact? Then you're going to kind of open the image file, perform some processing steps on them, make some kind of selection and segmentation, and then perform the analysis. And the analysis is when you're going to measure things in your images and store that data into arrays. And then you may want to save out the information in your measurements to end result images and log files so that you can then perform some statistical analyses on. So pretty much every script that I've ever developed follows this pipeline, and it's a pretty standard kind of workflow. Some hints for when you're scripting. Always save out your intermediate steps, your thresholds, your masks, your generated regions of interests. These are all really important for reviewing your results and troubleshooting and debugging your code as you run it. Use lots of annotations and well-defined variables for other people to understand. Don't just name them variable 1, 2, 3. Call it nuclei count 1, for example, with the comment that nuclei count 1 is for the region renaming of nuclei. remember, if you're going to plan to publish your scripts, other people need to understand them. So comment your scripts and describe the goals of what you're doing in each segment or block of code. So the code is may look daunting to some people. So we're going to walk through and kind of show some example code and explain that often there's these chunks that we always use, and that the scripting is just a series of blocks of tasks that you may repeat over and over. Certain parts of my scripts are always reused. There isn't much point in rewriting every component. For example, most scripts will include this at the beginning. The path is a variable that is chosen by the user. So where are the files? So if you point to a folder on your desktop, then the path would be, C, user, desktop, and then that folder. Then I run the command list or get file list within the path, and that's defined under the variable list. So this now creates an array with a list of all your files in it. We want a results directory, and that results directory is going to be in the folder that you have pointed to say my data here. We're going to create a folder called results. So we run the command file make directory results in that path. Now we don't want to always refer to path plus directory, so we have this variable results dir. Next, we want to decide if the script should run on the image that it's going to open or the file that it's up to. So we have a for loop. Now for loops will say, for some condition, do this. So we define a variable called I, and we set its value to be 0. So at the beginning, our variable I has a value of 0. And we ask if that variable has a value that's lower than the length of our list of files, then continue on. So this is the variable definer, this is the condition, and then we have at the end this bit that adds 1 to I each time the script runs. So if we had a list of 10 files, then I being less than 10 would run, and then I would become 1. It would do all these commands and then say, if I is 1, it's still less than our 10 files, so keep running. And eventually it would get to be not less than our value, and it wouldn't run anymore. When we have these loops, we have the squiggly brackets that then define the grouping of commands that will run within that loop. Now, next, we might want to have a filter. So you may have files that have .tiff, you may have files that have .text that are metadata files in your folder. So we want to say we only want to run on the file if it ends with the word or the phrase or the string in coding terms .tiff. Then we're going to run some commands, so whatever we want to do. And once it's done that, we're going to close off these loops. So we have a for loop, and then nested within it, we have an if statement. So our file list of 10 files may only have 5 image files and 5 text files. So it's going to run this loop 10 times. But if it doesn't end in .tiff, it won't run this section where we do things, so that you're not opening or trying to run a maximum projection on a text file, for example. So the commands might only run the number of times that you have files with .tiff, but it will check over everything in that loop. And then once we're done, we have the closed squiggly brackets. So your example code will look like this. You've got a folder that you want to start, where your files are. You want to get what files are in that folder. We're going to tell it that we want to make a folder called results within our directory, and then it goes and makes that folder. Then it says for the files that are contained in that directory, if it's less than the total number of files and it ends in tiff, then do this. Now we could change TIFF here to be whatever we want. Now, something you may, or a command that you'll see is the get title. So before, when we had the batch command, we showed that we don't want the file name to be hard coded in. We didn't want to keep looking for that one file. So what we can do at the beginning, once we open the file, is we can say, well, let's get the name of that file and call it a variable called window title. Then, whenever we want to refer to the current open window, we can just call the variable window title. And this will make a little bit more sense when we go through some example code. Now, one thing that often might trip people up is if you're using bioformats to open your window or your images, you'll get the bioformats configuration window that pops up. So it's going to automate through your folder of 100 images, but you don't want the bioformats opener window opening 100 times. So you can go into plugins, bioformats configuration, go to the formats tab and scroll through the list. And if you're using, say, a Zeiss CZI image, you can find the Zeiss CZI and tick windowless. That way it won't pop up that opener window for every file. And so your script will run rather smoothly. That's a tip. So I have a script that I've written that I've provided in the folder, and we're going to call it the batch Z projection script. Now we could just do this as a maximum projection batch process in the way that we showed previously. But maybe not every time we want to do a max projection. Sometimes we might want to perform a minimum projection, or we might want to perform a sum projection. This way, we can do it using a script, and it'll be a lot more lines of code than in the batch processor, but it gives us a bit more flexibility. And you might want to take this code and use it in your own workflows so that you can quickly batch project lots of images. So often I found that our researchers were spending lots of time capturing Z-stacks on confocals and wide field microscopes, and they had lots of fields of view and they wanted to find a particular image to then make their figure. Rather than having to go through each file one by one, max projecting it, and then seeing which one was the one they're after, I wrote this script to just quickly perform it on a whole folder of images. So this will speed up their workflow. One of the main kind of goals of doing a script. Rather than doing it manually, image by image, it's now automated. It takes a folder of images, it opens them one by one, performs a user-chosen Z projection option, and saves some outputs for them. So this is what the code looks like. We're not going to go through line by line, but I'm just going to kind of describe what these chunks of code are doing. So at the beginning of the code, we clear the log window. You don't want any kind of old information in there. Next, we have a license. So I include a license in my code so that other people can use it, can modify it, etc. And then we have a description. So we kind of describe what version of the code, when it was last updated, and what the goal of the code is. And we display a box that explains that information to the user. So we have this description information as defined variables. For example, the script title, what the description is all this text. Then we display that to the user. And this is the info box that's displayed. So this chunk of code here is what's required to display that information to the user. So if you install this script into ImageJ or FIJI, then you may not see the raw code. So this explains what it's doing. We have that information is also written into the log window. So to meet fair data principles. If we modify our data in any way, we should kind of have a record of what was done and when it was done. So the log window populates with what the script's called, when it was run, when it was written, what version the user ran, and the date and time that they ran the script. Next, the user is going to be asked to say, well, where's your files? So a warning box pops up that says, you know, this line of code. You're going to navigate in the next window to find your images. Sometimes you might have a subdirectory that's made in this folder, and maybe you need to take note of what the file extension is. So that's the code for this window. And then this code should look familiar to you. It just says the path and the list. So that's that 2 lines of code that always comes up before. Next, we have the parameters box. So we asked the user, they have a number of things that they can choose and chop and change when they run this script. So this is what makes it a little bit more flexible than just running, you know, projection type equals max projection in the batch process mode. So the script says, well, what's the extension? So it's going to ask you what your file extension is. So this is the parameters box. So before we say choose your file extension, we have to define what that extension might be. So the default would be .tiff, but maybe it's .czi. Then we have all these different commands. So we can add a message to the dialog box. We can have choices. So run Z projection. Well, max intensity is one of the options, but you can see that we've made an array with min intensity, average intensity, some slices, or no projection. So we can use this script to not actually project data. So just open it with bioformats and save it to TIFF. So rather than having another script that does convert to TIFF, we can use this code to do it for us. So this will display the parameters box, and the user can tick on and off different things and choose options. Then we have some code that kind of defines variables based on the user's choice. So we have a variable called projection type, and it gets the choice of the projection here. One of the options is to reset the brightness and contrast of the image. So we have auto scale as a variable name, and it gets the checkbox choice. We can save the file as an AVI, we can save TIFF output, we can concatenate all of the files into one AVI. So if you have a series of data where there's lots of Z stacks over time, well then maybe if you want to flatten each one, you string them together and watch in a movie what happens. And do you want to run it in batch mode? So batch mode is the ability to perform these tasks without actually opening and displaying the data. So if you wanted to open the big ZStack file, it takes a lot of time to actually visualize that. So if you just wanted to perform the numerical algorithms and modifications on the data, you can do that in the background in the script quite quickly. So then we get all these variables that the user defines, and we print it out to the log because we're good researchers and we want to say what we're doing. So we have this parameters section, and it says the projection method chosen, and it auto-populates it with the variable that was chosen from the box. So we've strung now the array choice into a variable, and then we've written that out in a print statement. We have some if statements. So if the user has ticked reset brightness and contrast, well then the auto scale value will be defined as 1, and it will print that it's turned on. If they haven't ticked it, then the variable here will be set to 0, and then the output will be printed that it's off. And this applies to all the other methods. Again, we have another if statement. If batch mode was ticked, then it's going to run the command batch mode equals true, and it will print it's running in batch mode. If the user said that they wanted to use the AVI, or that they wanted to concatenate into an AVI, so if either of these are set to 1, then create the AVI parameters box. So the AVI parameters saving box will ask you what type of compression you want to use and what frame rate you want to use. So it has to have some variable here. So the frames per second is just set to 10, and the dialog box asks, well, what's the string? What's the frame rate in FPS? It then scrapes that information back into a variable so that we can refer to that later on. Okay, now we're getting into, once everything's set up, we want to get the internal time and the date and time for now when we're going to run, because we get the date and time at the beginning, but maybe you spent 10 minutes or you got distracted. So the actual script runtime begins here, because now there's no more any user input. It will just run. We're going to create that results directory, and the results directory in this case is going to be within the folder, and it's going to call the folder projection type. So if you had max projection, then the results file will be called max projection results with the year, month, day, and time into a output folder. And then it makes that results directory. So rather than typing this big long string of information out all the time, we can just refer to results dir as our location to save things. So we have our loop. File opening loop is starts at 0, and is that number still less than the total number of files in our output directory, input directory. Next, we want to confirm that the extension that we defined is only the file that will be opened. Then we'll say open the file plus this iteration number of the listed files in the input directory. So the file will open, and we instantly will scrape the file window name, and we call that window title. Now, what I also do is I create a variable called window title no extension. So we scrape away the .tiff at the end or the .czi. And the reason we do this is if we don't have something like this, you can have files called, my example image.tiff.jpg or .tiff.tiff. And that gets a bit silly and a bit messy. So we want just the file name with no extension. We print out to the log file that we've opened file number, whatever, of the total list, and that it's called this name. And that's good for debugging. So if you have it's constantly crashing on a certain file, then you might want to go back and look at that file and see what was wrong. Now, did the user define that they want to reset display settings? So if they did, then what we do is we get the stack dimensions, we move to the middle of the stack, and we go through each channel where we reset min and max intensity. And we print that we've set auto scale for what channel. So it looks for how many channels there are, and it works through those number of channels. So if you have one channel, it'll do it once. 3 channels, it does it 3 times. We haven't defined how many channels you have. We query the image, how many channels it has. Because if we said, go to channel 3 and reset min and max, maybe the user only has a single channel image. So this is where the scripting is kind of looking at what it's given and deciding what to do. So the next part is we gave the option in the input parameters box to perform no projection. So if we have no projection turned on, then it's going to print out to our log that we're not performing a Z projection. If we're saving as a TIFF, then it's going to say, okay, saving this file with this no projection type as TIFF. And then we know that it's done, it's closed off those loops, and it moves down to the next blocks of code. So if the projection type doesn't equal no projection, then the user's input some projection type. So it will perform, it prints that it's going to perform this projection type. And it runs that command, which you may remember from before, was run zproject projection type equals the variable because that variable is populated from earlier on in the script where they said, I want to perform max projection or sum projection. Now, conveniently, those variables that are chosen there are the exact same parts of the command options for this run Z project. If TIFF was turned on, then it will run that same little block of code, saving TIFF, and saves it as a TIFF. If we had save as an AVI, so if AVI variable was equal to true, i.e. the users ticked it, then if the number of frames doesn't equal 1, then save it out. So you can't save an AVI with 1 frame, so that's why we have that little conditional statement, and then it does it and closes the window. Now it's reached the bottom of the code, so we have this little block, which is another type of loop called a while loop. So while the number of images open is greater than 0, we're going to run the command close. So if there was 3 windows open, that's greater than 0, it closes it. Then it says there's 2 windows open, that's still greater than 0, close it, etc., down to no windows left. Then we close all of our loops that we had at the beginning. Now we haven't finished the script yet because there's the option for us to concatenate all of these files back together. So if this variable concatenation was set to true or 1, then it's going to write out that it's going to perform the concatenation. So it's going to open using the image sequence, which I showed before. So it's going to look at a folder and open all of those frames. And it's going to open the files from this results directory that ends in TIFF, and it's going to sort them numerically. Then it's going to run the command save as AVI with the compression type that we defined before, the frame rate defined before, to a location in the results directory called concatenated movie of window title, no extension, .avi. Then it's going to write out to the log that it has finished, and it will work out the time it took to run. Then it's going to take that log window and save it to the results directory. And lastly, it's going to come up a pop-up on the user's screen that says batch completed, so that the user knows that the script finished and ran to the very end, had no errors. Now you have a log file that looks something like this, where it has, the macro name, some information that I wrote it. These were the settings that were chosen. And you can see for each file, it said opening this file 1 of 65. This was the file name. It set auto scale for channel 1. It performed a Z projection, and it saved that projection out as a max projection. Then it did file 2. And you can see in the output file list, we have all of these files. We have the concatenated movie of files at the end and the log file. So I've given you this script. It's located in exercise 6. There's a folder in here that may be zipped that is contains a series of ZStack files. So we're going to open and run the FIJI script to familiarize yourself on how this tool may speed up your workflow. So there is, it's quite a significant amount of data. So I did zip it, so you may need to decompress it first. So we're going to run our batch projection script. So in that exercise files, exercise 6, we have our example scripts. Now I've given you 2 scripts here. I'll explain the second one in a minute. The directory Z projection script is what we're interested in. Now, if we open the script, the .ijm, it loads it into this the script viewer, and you can run the script from here. That's fine. So you can click run. We get this description window that explains that it's going to take 3D or 4D images, and it's going to perform a Z projection, whatever type you define, and output them. You can filter the files by some extension using the bioformats importer. Files to be processed should be within their own directory, and the processed images or movies will be placed into a subdirectory called projection type _ results with the date and time. The script can also be used to convert files to TIFF by selecting the no projection option and save to TIFF outputs. Checkbox for concatenation will combine all outputs into a single AVI file, suitable for lattice light sheet datasets, for example, and that a log file will be saved within this directory. Next, we get that warning. Use the next window to navigate to your directory of images. Note that a subdirectory will be made within this folder for output files. Take note of your file extensions. So we are going to go to exercise 6 in that data folder, data. Now this folder contains all of these TIFF files. And these TIFF files are 160 megabytes each, and we have 60 of them. So we will be processing here about 10 gig of data. Now it's going to ask us what steps we want to use. So we want to perform a max projection. They end in this extension .tiff. We can reset the brightness and contrast. We want to save each individual file out as a TIFF, and we're going to concatenate them into a movie while running in batch mode. So once I click this, there's no more user input. It's going to run. Sorry, there's the API parameters. So we can leave that as the defaults, and then it will run. We can see down here, our log window is updating. We can also see the status bars saying reading and saving quite quickly. But in a very short period of time, we can process these 60 images or 10 gigabytes of data in a minute or two. I've not sped up the time here. That just ran and took 27 seconds to process. We can go back into that folder, and we can see that there's a folder being created called Max Intensity Results with the date and time that it was run. Now we can see that individually these files have been max projected. And then I have this concatenated movie, which we can open using VLC or any other video program, and we can see what's going on. I also have this log file, which has been saved. And this is straight from the login FIJI. Exit the video. That we have this title, the version date. So you can see this was made in 2019, and that it was run today on the 7th of May. These were the parameters that I used, and we can see that for each file, it ran, it did what we asked it to, and then it saved them out, and it took that long. Now, the second script that I gave you in that example scripts file is what I call the script shell generator. What this is this is a script that generates the text required for a script for you. So you can say, run this script, and it asks you some information. So what's your name? Perhaps your name is Homer Simpson. And you have an email called jblogs@yahoo. You have a title, My Awesome Script. And we're going to call this version 1. Blah, blah, blah. So you'd write your description. And my script is going to open CZI files. And I want to do some tasks and get some measurements. And then I want to put those measurements into a spreadsheet. So I want a summary file as well. And if I click OK, the log window populates a whole heap of text. So we can select all of that, copy it, make a new script, paste that in, and then change the language to the IJ macro, ImageJ macro language. And what you've been given with this script is that's the chunky peripheral code so that you can then add in your commands. It's put who you are, the title, who made it, all of this information. You can see that it was made by this person, this is your email, the license information, and blah, blah, blah. It auto-populates this bit that says, use the next bit to go to your window. It brings up a file browser to find your files. If you want any parameters, we can just run this subset of code here to show you that it brings up the box for if you need to change from CZI to something else. It creates a results directory within that location, and we have this new little bit of code that we haven't really seen before, but it creates a summary file, which is an Excel spreadsheet in the results file. Now I save it as an Excel spreadsheet, but it's really just a tab delineated file. And so it's going to print, to the summary file, some heading columns, and you can change these to your heart's content, but you may want to grab the image name, the image number, the number of objects that you found, the object ID, and maybe then like the mean intensity or something. But you can add as many here as you want, each column separated by this /T, which is the escape command tab. And then we have our loop. We have the opening stuff where it gets all the window names and it prints it out to the log. And then basically I have this insert script here. So this is where you'd put your macro commands. Now, I've written just at the end here that it's going to print back to that summary file, the window title, so the file name, this variable Z, which is the loop number. So if it's image 1, then it will print Z1. You're going to have to define some kind of object here to print. So the number of objects needs to be defined somewhere. So if you run analyze particles, then you might have 50 results. So you can run the command n results. So then that would be the number of objects, the number of results. Then if you iterate through each one of them, you could have a variable for object ID. Have a look at some of my other code that I've got on my GitHub or other people's code to get some ideas here. But then lastly, it writes that out, saves it as a TIFF for the output, and closes all the windows and prints out to the log. So if you didn't want those spreadsheety stuff, you just run that command again without ticking the summary file. Go to the log window. Paste all that in there. This code doesn't have the summary file stuff. So this is just a big wrapper to help turn your batch commands into a bit more, dynamic code. Use it to your heart's content. Okay. Bring back the slideshow. So scripting in FIJI can be as basic or advanced as you need. Search online for other people's macros and scripts that people have written and modify them as required. My scripts are all publicly available on my GitHub page where you can go and download them. This is my GitHub page. Under the repositories, we have a whole heap of different code that I have. So some of the useful FIJI code, for example, has a bioformats TIFF to JPEG, cell pose masks to ROI managers, crude time point standard deviation, a rolling average, and headless Z projections, and the script shell generator. I have code that we've published where we find bacteria and measure all the channels. So if you wanted to look at how do you scrape results and put it into a spreadsheet down the track, have a look at this code. I try to provide readmes, and the code is quite well commented, and we can see, you know, again, this should all look familiar. It's the same chunks of code followed by the actual meat of the script where it does things. And in this case, it splits windows, it runs some measurements, it does some massaging, it creates arrays or tables to throw data in. And then it goes and scrapes data from the results window into those arrays. And then we print it all out into this big long string that is each line of the spreadsheet. So hopefully this will get you interested in coding. Okay. Thank you for watching this workshop on advanced FIJI. I provide my contact information here. I am on Twitter, my GitHub. The IMB Microscopy has a YouTube page where we have other tutorials on how to use microscopes, some FIJI workshops, some Imaris workshops, FLIM workshops. We're adding more each time we run these things, and that this work wouldn't be possible without my support from the Chan Zuckerberg Initiative, and the facility is supported by ACRF and the Australian government via the Australian Research Council and the National Health and Medical Research Council. Thank you.